I would like to start my presentation with something that is a bit depressing. As you all know, we currently face a huge environmental crisis. The average temperature around the globe has increased by 1 degree Celsius, and it is expected to increase even more in the coming years. This, although it might seem like a small change, it has significantly affected the survival rates of many animals around the globe. On top of that, we have plastic waste, which is a huge issue in many parts of the world, especially its accumulation in different environments. So this is a global issue that requires a collective action. Fortunately, the United Nations climate meeting in Paris in 2015 tried to address this by compiling the 17 Sustainability Development Goals. And in most of those, the renewable materials has been the key. So in order to drive our society towards a sustainable future, we need to replace the fossil-based resources with bio-based ones. And specifically, a really nice candidate to do so is to use wood biomass. Within this context, Sweden plays a crucial role. 70% of Sweden is covered with forests, and Sweden is known as one of the world's largest exporter of pulp, paper, and sawnwood products. So wood is an excellent candidate in this context to replace fossil-based resources. Wood is a natural biocomposite where we have cellulose fibrils reinforcing a matrix comprised of hemicellulose and lignin. And these cellulose fibrils are comprised of cellobiose repeating units, which are characterized with less ordered and ordered regions, which upon mechanical and chemical treatments, they either loosen up, so we can obtain cellulose nanofibers or CNFs, or we break down these amorphous and less ordered regions, so we can obtain cellulose nanocrystals. Cellulose has excellent properties, some of which are summarized here. And this is the main reason why cellulose, or one of the main reasons why cellulose has been used in a plethora of applications in our everyday lives. But there is a trick here. In some applications and in some material perspectives, cellulose must coexist with other polymeric materials. And this can be challenging for two main reasons. We want to have cellulose, which in this case is represented schematically in a simplified way as a red sphere. We want to have cellulose well dispersed in a liquid medium. We don't want to have it aggregated or even precipitated. And on the other hand, we want to enhance the compatibility of the hydrophilic cellulose with hydrophobic polymer matrix materials that are currently used in order to make composites. There are many ways in order to approach this. One way is to use chemical or covalent modification techniques, where we can have the grafting of polymeric chains on the surface of cellulose, which will force cellulose molecules further apart from each other through steric stabilization, or we can introduce charges on the surface of cellulose, which will have the same effect as steric stabilization, but this time through electrostatics. These type of chemical modification techniques are applicable because of the great number of hydroxyl groups on the surface of cellulose. However, large amount of solvents, many processing steps, and in sometimes it is difficult to characterize the modification that was performed. So in order to bypass that, we can use physical or non-covalent modification approaches, where we can either have polymeric chains or polymer nanoparticles that are physically adsorbed onto cellulose, which will further increase the compatibility or enhance the compatibility with other polymeric materials. This is a relevant technique industrially because it has already been used, for example, in the paper processing. However, and on top of that, it has been the main objective of this thesis. We have prepared and synthesized polymeric nanoparticles, highly tailorable, and we have utilized them in order to physically modify cellulosic surfaces. Typically, these polymeric nanoparticles, commonly known as nanolatexes, can be prepared via Malmström polymerization, where we have low molecular weight surfactants, where are comprised of hydrophobic tail and a hydrophilic head. And when dispersed in water above a critical concentration, we can get these micelle structures. And inside the core of those micelles is where the polymerization of a hydrophobic monomer takes place. However, there is no covalent bonding between the hydrophobic core on those micelles and the hydrophilic shell that covers them. and this can lead to some unfavorable effects. So we need to find a way in order to covalently link a hydrophilic polymer chain with a hydrophobic one. And in this thesis, we have used a controlled radical polymerization technique known as RAFT, which stands for reversible addition-fragmentation chain transfer polymerization. In this case, we have used a chain transfer agent, also known as RAFT agent, which controls the molecular weight of the final polymer. This RAFT agent is comprised of two groups. We have the Z group, which provides the stability on the RAFT agent by controlling the reactivity of the thiocarbonate bond, and the R group, which is known as the leaving group. During RAFT polymerization, because of these rapid addition and fragmentation reactions, this R group leaves the RAFT agent, and it is responsible for further propagating the polymerization. In this thesis, we have combined RAFT polymerization with a technique that is called polymerization-induced self-assembly, or PISA. It is a two-step process, where in the first step, we polymerize a hydrophilic monomer in water in order to create a hydrophilic macro-RAFT agent, which in the second stage, we chain extend in water with a hydrophobic monomer. This will create an amphiphilic diblock copolymer, which above a critical ratio between the hydrophilic and the hydrophobic blocks, it will self-assemble into nanolatexes, which will evolve in size until the end of the polymerization. This RAFT-mediated PISA technique is highly versatile because you can target the charge density and size of the nanolatexes that you prepare. You can play around with the glass transition temperature of the core and the cell components that you used. You can have different morphologies. You can have spheres, worms, or vesicles. And the final nanolatex dispersions are quite stable. These PISA nanolatexes have been explored in many applications in the literature, and quite successfully, if I may add. And the true pioneers of this technique has been a group in Lyon led by Lancelot and D'Agosto, and another one in UK led by Stephen Arms. These two groups have expanded quite a lot our understanding on how the systems work and how we can optimize them and tailor the final properties, but there are still some challenges that remain with regards to their morphology, to the parameters that affect the absorption of such nanolatexes onto different surfaces, and also to their composition, all of which we have tried to address in different projects in this thesis. So for the first part of the presentation, I will focus on the morphologies that we can obtain by using this RAFT-mediated PISA technique and how we can tune these features on demand. Then I will move on the utilization of PISA nanolatexes in order to modify cellulosic surfaces. And I will finish on presenting some opportunities on how you can replace fossil-based materials that are comprising these nanolatexes with wood-based ones. Focusing on the morphologies of PISA nanolatexes, we have prepared macro-RAFT agents which are comprised of protonated PDMIMA and long hydrophilic oegma units. And we have chain extended them in water with MMA in order for the hydrophobic block to prepare these nanolatexes. And this system has enabled us to study the degree of polymerization of each block, the length of the oligoethylene glycol side group, as well as the pH of the dispersion and how these parameters relate to the final morphology that we can obtain. We found out that when the macro-RAFT agent that we used was comprised of more oegma than dimaima, and when the length of the oligoethylene glycol side group was the longest, then we have rich morphologies. We can have the coexistence of spheres, worms, and even vesicles at different time intervals of the polymerization. We realized also that when we increase pH, the pH of the dispersion, and we go closer to the pKa of PDMIMA, which is approximately 7.8, then these nanolatex dispersions, even though in some cases they retain their morphologies, they either aggregate or precipitate in some extreme cases. So this is something that we need to look further into the future. Previously in our group, we have prepared monomodal and monodispersed nanolatexes that are comprised of a protonated PDMIMA cell and a hydrophobic PMMA core, where the Z group of the RAFT agent that we used was an aliphatic chain. However, when we prepare nanolateces with exactly the same chemical composition, but with a Z group, which is a carboxylic acid instead of an aliphatic chain, then something very interesting happened. We saw that we could prepare bimodal reproducible nanolateces. As you can see, we have two different populations. We have large and small nanolateces coexisting at the same time, at different time intervals of the polymerization, which both populations increase in size until they reach a plateau, which indicates also the end of the polymerization. This technique and this feature in the literature, it is considered as lack of control of the RAFT polymerization. However, it makes you wonder why this is considered lack of control when this feature is quite reproducible. So in order to demonstrate the advantages of such reproducible feature, we adsorbed these bimodal nanolateces onto silica wafers, and we evaporated the water in order to create these iridescent and opal-like structures, which are a result because of the difference in size. As you can see, we have large and small nanolateces coexisting, and because of their arrangement on the surface as well. So in the literature, you can obtain exactly the same feature only by mixing two differently monodispersed nanolatex dispersions at different ratios. But we were able to do so by a single pot reaction. Now that we know how we can tune these morphologies of PISA nanolateces on demand, we wanted to investigate and understand better how we can optimize our system in order to affect and influence its adsorption onto cellulosic surfaces. In the literature, this has been studied quite a lot. However, the main challenge has been how you can decouple the parameter of charge density and size of nanolateces, because these two parameters are interconnected. Because by increasing the size, you usually decrease the charge density of the nanolateces or the nanoparticles that you use. Fortunately for us, by using this RAFT-mediated PISA technique that I explained earlier, we were able to decouple these two parameters and study them separately. So by adsorbing these nanolateces onto silica or onto regenerated temp-oxidized cellulose model surfaces, we monitor their adsorption with refractometric and gravimetric techniques. In the case of silica, we found out that the main parameter that affects their adsorption was that of charge density. By reducing the charge density, the adsorbed amount was found to increase. However, for the case of cellulose, things are a bit more complicated. We found out that both the effect of size and charge density are equally important parameters, because in order to optimize the adsorbed amount, we had to reduce the charge density and increase the size at the same time. In other words, in the case of silica, when we have a charged particle that sits on that surface, if that particle has low charge density, this means that the nanoparticles can sit closer together, so further optimizing their adsorption. Whereas the opposite happens when we have a nanoparticle with higher charge density or a really big nanoparticle. In the case of cellulose, we have what is called the volumetric distribution of charges on that surface. So when we have a particle that sits on that surface and it is charged, it can reach the charges that are further and deeper down into that cellulose surface. And cellulose, because it tries to compensate the charges of that adsorbed moiety, in some extreme cases, if the nanoparticle is highly charged, it can lead to the deswelling of the cellulose, which we have also monitored in this study. In this case, we have used in practice the information that we got from the previous study, working with model surfaces, in order to prepare nanocomposites based on CNF and low content of nanolateces. We found out that the contact angle against water of these nanocomposites was increased both for high and low loadings of nanolateces, whereas the opposite happened for the swelling degree. But what was quite important and interesting to us was that the mechanical and thermomechanical properties of such nanocomposites were increased only when we used a low content of nanolateces, and they were deteriorated when we increased the content. In order to understand why that happened, we have to look into the different interactions of the two components that we have in that nanocomposite. So apart from the CNF-CNF and nanolatex-nanolatex interactions, we have the nanolatex and CNF interactions. In these type of interactions, the distance between the nanolateces on the nanocomposite and how well these nanoparticles are dispersed in this film, it is quite crucial, because the further away these nanoparticles are from each other, the further the electrostatic interactions between the nanolatex and the CNF are improved, so we can have some sort of a toughening effect to the final nanocomposite. Because these nanolateces, in a way, act as cross-linking points between the CNFs. In order to address these sustainability development goals and trying to move away from these fossil-based resources, we tried to utilize wood biomass. So we focused on the wood-based and hydrophobic core, and we used the terpene-derived or alpha-pinene-derived sobrerol after a short methacrylation that we performed. We were able to prepare spherical nanolateces both by using a Malmström polymerization, where we used a low molecular weight surfactant, and also by using RAFT-mediated PISA, where we used a higher molecular weight macro-RAFT agent. In both cases, these cationically charged spherical nanolateces were adsorbed onto cellulose filter papers, and they were annealed at 150 degrees for a certain amount of time. We found out that we were able to expose this submac core and create a really nice hydrophobic polymer coating on top of these cellulose filter papers, which, as a result, increased the contact angle against water. However, we also noticed that in the case of PISA nanolateces, we have these spherical aggregates, even after 8 hours of annealing, which is quite excessive. And we hypothesized that this was a result of the structural stability that was imposed from the higher molecular weight macro-RAFT agent that we used in the case of PISA. When we focused on the hydrophilic shell of these nanolateces, we used the glucose or glucuronolactone-derived gamma monomer, and we prepared spherical nanolateces with quite good control of their size. However, we realized that when the macro-RAFT agent was comprised of a few units only of this gamma monomer, this macro-RAFT agent was not hydrophilic enough to sustain the long and quite big hydrophobic PMMA core that we used. So in order to bypass that, we copolymerized gamma with diMIMA, or in other words, we added some sort of cationic charges on the surface of these nanolateces, which further improved their electrostatic stabilization. In order to showcase quite briefly a potential application of such partially wood-based nanolateces, we have focused on this great number of hydroxyl groups on the case of gamma. So we targeted the elimination of copper ions from solutions. Fortunately for us, we were able to have a positive complexation reaction between these partially wood-based nanolateces and the copper ions in solutions, especially in the case of small nanolateces, which means that we have a higher surface area and greater number of these hydroxyl groups on that surface. So in order to conclude this presentation, we have studied different morphologies of PISA nanolateces. We have prepared spheres, worms, and vesicles with pH-responsive cell polymers. And we also prepared bimodal reproducible nanolateces in a one-pot fashion. And we studied the importance of size and charge density of PISA nanolateces and how we can optimize these features in order to tailor the adsorption on different surfaces. And we use that information in practice in order to prepare CNF nanocomposites with low content of these PISA nanolateces. And last but not least, we try to replace fossil-based components that we used for the preparation of these PISA nanolateces with wood-based ones. And we focused on the terpene-derived core and glucose-derived shell. And we briefly showcased a potential high-end application of such nanolateces. So for the future, I think it is quite important to expand and create a library of these bimodal nanolateces now that we know how we can tune this feature on demand simply by playing around with a tiny chemical group of the RAFT agent. Also to use worms instead of spheres in order to modify cellulosic surfaces. And it would be interesting to see how these worm-like structures affect the stability of cellulose in dispersion, but also the compatibility with other polymeric materials. Oh, sorry, mistake. and also to post-functionalize the double bond that is in the repeating unit of PISA-nanolatexes, and further optimizing the template that we used for the metal ion capturing applications. I think also to finish that it is quite important to introduce a lot more bio-based materials to replace these fossil-based components that we have been using. And why not combining this gamma shell and PISA core and create the first fully wood-based nanolatex? With that, I would like to acknowledge Knut and Alice Wallenberg Foundation for funding my PhD for the past 4 years. Of course, all of my friends and colleagues at the Coating Technology Division at FPT and at Wallenberg Wood Science Center, my super amazing supervisor, Professor Eva Malmström, all of my co-authors on this incredible journey, and thank you all for your attention.